All right, there we go. All right, so let's take a look at this one. It says, for what value of k, if any, will y equal k sine 5x plus 2 cosine 4x be a solution to the differential equation y double prime plus 16y equals negative 27 sine 5x? There's a couple of ways you can do that. I mean, obviously, we could just plug in the different k values they give us, which would work. We could go ahead and just find the second derivative and work our way that way. So let's see. I think that's what I'm going to do because y'all know I'm kind of procedural. All right, so that would give me 5k cosine 5x minus for y prime. Oh, there she is. Minus 8 sine 4x. I'm coming. Oh, thanks. All right, text Laura, tell her we have her stuff. Somebody found it. Okay. Is she back there with you, Gareth? No, I mean, like, is she she will be, that's what I meant. Nope, she's not. Nope, not right now. Okay. Okay. All right, so sine 4x. Okay, and so then if we did y double prime would equal 25k or negative 25k sine 5x minus 32 cosine 4x. Did y'all get that? Yep. Okay, so then we're going to take y double prime, so negative 25k sine 5x minus 32 cosine 4x. And then we're going to go do plus 16 times y, so that's going to give me, I'm just going to add it on, plus 16k sine 5x plus 32 cosine 4x equals negative 27 sine 5x. Now, I did all that because I'm going to lose those 32, so there's a negative and a positive. If I have negative 25k with the sine 5x plus 16, does that leave me negative 9 sine 5x equals, yeah, I forgot the k, thank you, negative 9k sine 5x and negative 27 sine 5x. So because the sine 5x is there, we can drop that, and we get negative 9k equals negative 27, or k is equal to 3, which is that D. Okay, so again, just an exercise in algebra when we're dealing with those problems. Okay, question about that. Okay. All righty then. So here's our affirmation. There are no shortcuts to any place worth going. But okay. So today we're going to talk about something called a slope field. And so that's why you see these little graphs up around the room. We're going to actually create some here in a little bit in our groups. But before we do that, let's look into a little bit of an investigation so you can play with it a little bit, called Seeing is Believing. If you remember, we did toothpick tangents to estimate slopes on a curve last semester, all right, where we took the toothpicks and we laid them down. How might they help us this semester? If we'd had many toothpick tangents, could we approximate the original curve? So we're going to explore. So what I want you to do is to take a second and work through this. I think there's only 5 questions, okay? So it's just asking you about the differential equation. What does each dot on this derivative graph represent? And all that good stuff, okay? Ready? Go. I like the glasses.
Thank you. They're not real.
Oh, are they not?
They're not at all.
They're an aesthetic, huh?
Yes.
Okay.
They're stylistic.
Okay, I like it. I had to get new glasses Friday. I was appalled at what they cost. It's okay.
Mm.
Yes, to get progressive lenses so that I can actually see at all distances. Okay, old people glasses are expensive.
Old people's glasses.
Yeah, I mean like $700. I was like, oh my God, are they made of gold? It's almost $700. I was like, no. Good thing I don't get those, but like once every 10 years.
You want to see it cost the same as an iPhone.
I mean, seriously. I was like, dang. And that doesn't even include my contacts. I have to order them separate. Oh, there she is. It's right there with the girth.
It's like, I just like came off.
Yeah. So it must have went out your window and somebody found it.
Guess so. I was frantic.
But life is good.
Morning, everybody.
Plug the point into the differential equation. You're getting the slope at each of those points. So you're going to plug that into your differential equation to get the slope.
Hello.
Oh, I like your shirt. It says senior at the top. Oh. You say it doesn't look good. You actually look like Warby Parker.
good. It's all good, Joel. You don't have to worry about it. It's fine. Fine.
I'm starting to worry about it.
Right, when you get to the back side, you're gonna graph little bitty line segments, like they're little bitty toothpicks that have those slopes that you found in the chart. So like they're mini toothpicks. All right, let's look and see what we got. So it says if we look at this differential equation given by dy dx equals 2x, what would each dot on that derivative graph represent? The slope of the tangent to the curve at that point. Okay, so it would be the slope of the tangent to the curve at that point. That's what a derivative is. It is the slope of the tangent. And so if we take our differential equation, dy dx equals 2x, and we fill in the slopes at that point, all we're going to look at is the x coordinate. So I would get -4, -4, -4, -2, -2, -2, -2. Double 0, I'd get 0, 0, 0. Double the first one, I get 2, 2, 2, and then 4, 4, and 4. Okay, so they just pick some random points there, and we literally plug it into the differential equation. We're doubling the x value. Okay, now on that next page, I'd ask you to do something pretty specific. Okay, it says, hey, let's actually draw in those little bitty toothpicks. Okay, could we fill in the rest of the points based on the patterns that we see? Okay, so let's do the easy ones. Let's do zeros. Okay, at 0, 0, I had a slope of 0. How would I represent the slope of 0? Yeah, a little bitty horizontal line. And that's going to be true everywhere x is 0. Okay, and so x is going to be 0 all the way up and down this y-axis. Okay. Now, if we do the positive side, then it tells me that everywhere where x is 1, what's the slope going to be? 2. So it's going to be a little steeper than 0. Okay, we're not going to get it perfect. We're just going to guess as we go up through here. All right, but they should all be parallel because they'd be 2. All right, what about where it's -1? -2. So we're just going to switch it. Okay, so -2. Okay, and then what about where x is 2? 4, so it'll be a little bit steeper. And then where it's -2, be -4. Okay, again, we're not going to get it perfect, but we could try. And then what about where x is 3? It'd be 6. It'd be even steeper still. And on the other side, -6. Okay, now, one of the ways that we can kind of get used to drawing those is to draw in the easy ones first, okay? 1's pretty easy to draw. 2, one of the things we can do is think about, if we look for this green line, if I go up 2 and over 1, those 2 dots should be kind of aligned. Now, mine aren't perfect, obviously, okay? But it's a way to kind of help you. If you've got a small straight edge like your ID, it's a nice thing you can use to kind of line it up. Now, the good news is AP rarely ever asks you to fill out one this big, okay? Usually they'll give you part of a grid and be like, fill in 6 dots, okay? Like, or fill in 8. Like, so they won't ask you to do the whole thing, all right? So just know that. And they're usually pretty intentional about which points they choose so they can see the definitive, do you understand what the slope is at this point? This is called a slope field, all right? It's where we take the little bitty slopes at each point, okay? It's where we sketch the slopes at each point, okay? And we use our differential equation to figure it out. Right? Now, in this differential equation, what's the only thing that impacted my slope? The x value, okay? Differential equations can be very complex, okay? This one was pretty simple. We were just looking at a differential equation that only depended on x. Now, what we have here is beautiful. We want to sketch a curve that follows these slopes, okay? So basically what I want to do is I want to draw a picture in somewhere that follows these slopes. So I know if I have a 0, let's use the point, let's say 0, -1, okay? And I follow the slope pictures on each side. What should be true on each side of my picture around that point? Oops. Yeah, it should be symmetric, right? So wherever I draw it, I need to be sure it's symmetric. How many curves could we draw like that? Infinite, okay? We could draw infinite. Okay? And the reason, why can we draw infinite curves? Yeah, okay, because there are infinite values on the coordinate plane, so it should grow. What we're actually drawing are solution curves to the differential equation. Okay. And we know it because there are infinite locations on the coordinate plane. Okay. So a slope field, it's showing me all those solution curves to the differential equation. And what do all of our solution curves vary by in a differential equation? A constant, right? They differ by that vertical shift. So let's use our differential equation and let's find a general rule. And let's see if our curve, our picture that we got supports what we found. So our differential equation was dy dx equals 2x, okay? If we take an antiderivative, what would y equal? X squared plus c. Does our picture look like, oh, too far. Does our picture look like a quadratic, all right, that varied by that vertical translation? And it does, okay? And so that's what a slope field is for, okay? A slope field is just a way for us to identify or draw a picture of all the solution curves to a differential equation. Let's see if the mouth and tongue can work today. Okay, so a slope field. It is a picture of all solutions to a differential equation. Okay. We construct it using tiny line segments. That model the slope of the curve at each point. Okay, and so we use dy dx. Okay, now there's only one kind of caveat to this in terms of what they expect from you at AP. Okay, would it be possible, depending on what kind of differential equation we had, that we could get an undefined slope? Sure. Okay, if we divide by a 0, we could for sure get an undefined slope. Or if it had like a y plus 1 or an x plus 1 on the bottom, there would be places where we would get undefined slope. According to AP, we draw no line segment for an undefined slope. So you just leave that one blank. Okay, and if they ever show you a slope field and you don't see a line segment at that point, you're to know that that stands for something that's undefined. Okay, so that's their thing for that. Because in my head, I'm thinking, we'll just draw a vertical line right there, it'll be fine, right? But they don't want that. Okay, so let's don't do that. All right, now there's some vocabulary that's specific to a slope field, and we're going to talk about it in a second. But before we do that, we're going to do a little group activity. Okay, So you notice that I have all the graphs up around the board. There are 25 points on those graphs. Okay, so I'm going to give each group a pack of Wiki sticks. They're brand new. Okay, you'll need to divide them into thirds. So if you need a knife, I'll get a plastic knife out for you to cut them. Okay, so that you have enough because there's 10 in here. Okay, but you get to pick your differential equation. Okay, little Russian roulette. Pick wisely. He's doing it. Okay, that's the one your group is going to do on the. Oh.
We got a couple in it. You know where Connie's at? Which is not bad.
Okay. Okay.
That's what I'm hoping. Do you feel like ever yet?
Right.
I don't feel like it anymore.
People's lucky.
What do you guys got?
Okay. All right. So what I want you to do, come up here and pick up a pack of Wiki sticks. Okay. And then go to your graph. All right. And you can do your calculations on the piece of big graph paper if you need to, or you do them in your head. Okay.
Orange.
Oh, Oakley's gonna miss this. I'll go green. Just feel like I'm
Okay. And you're gonna put they should stick to the paper for your line segment. Okay. And then we'll talk vocabulary. So group 5, so 4 and 5 are on this side. 1, 2, and 3 are over there.
Oh, yeah.
It's getting sticky.
Okay, that was pretty good.
I'm
gonna give you that All right, I put some knives out here if you need to cut your Wiki
Yeah,
sticks.
sorry, guys. Sorry.
That's fun. Hey, Parker, y'all are over here.
Number 4.
Yeah, y'all are group 4.
Bye, guys.
I
Bye,
thought
guys.
it was number 2.
Okay, I was like, okay.
I think it's like. Sam, why didn't you
Sam,
group
what
us?
did
Oh,
you
dude.
Like, we cut it like,
Okay.
Yeah,
so, okay.
yeah, you're gonna need to cut it in thirds.
Okay. Let's go 0, 0. It's gonna be over 0, so we're not gonna put anything there. Actually, anything on this line, I'm not gonna put it.
I'm getting it done.
You having fun taking it out?
Yeah, there's
I don't even know what that is, to be honest. It's Wiki stick. It doesn't, you ain't never heard of them. They're wax sticks.
You gotta get it to your own table.
Yeah, children's movie, bro.
I'm glad you were.
The haterade.
Yeah, because we're poor. I mean, me too. Oh. I cut trees into forests and build forts.
We start calling it.
It's okay, we're not gonna put them back in that bag, so you can bring it back.
Oh.
Yeah. I'm gonna
Well,
trash them.
then-
I bought 1,500 with these.
I think that, if you wanted to preserve the bag, that still would have worked. Well, it would have been inside out, and I didn't want to do that. You could have uninside out.
Yeah, but you'll need to split it.
No, so on all the ones where y would equal 0,
It might be easier to take them off one at a time and then.
Low-key was just right there. There's wax all over my fingers. There's wax all over my fingers.
Great haul.
We need a knife.
I don't know why that.
Thank you.
Powers are negative. They're both negative, so 5
Oh, thanks.
minus 1.
Okay. I will, thank you.
I'm bad at this.
Careful. We did it. Okay. One.
You wanna hear?
We're gonna go 0, 1.
Wrote.
0.
Getting no burrow.
0, 1. 0, 1.
Hey, Hey, pull them off one at a time, and then you can cut them a little bit easier.
0, 1
Oh.
would be 2 times 0.
Someone actually said the
Over 1, so 0. So negative 0.
Zero. No.
I think that's right.
Bruh.
Because we're just like that. Yeah, we got
Get
these
to cutting is crazy.
And it's a pretty good
I'm just gonna cut that chunk off. I don't really care about that.
Okay.
Yeah, Kanye's not.
There we go. And I'm gonna cut this in half. Oh gosh.
I'm pretty sure.
My kids are gonna be like,
No, I think it's fine. It's just taking.
Does anyone sit here?
no,
Okay, good.
it's just
We
me.
get to destroy it. For you.
Or no,
Right?
no, not like 20.
Oh yeah.
We'll do.
Oh yeah.
Which makes perfect sense.
We can honestly
See if there's 20. And then so.
Gracias very mucho. That's not how you would say that in Spanish, but
That's
whatever.
okay. I'll take it. Only me.
We're making sure that.
I knew.
Yeah, I was supposed to.
Well, okay, Samuel knows.
I
I don't know Spanish, but like, I know that's not right.
Anyone in here who took sophomore Spanish might know that that's not. I don't know.
-2,
Yeah.
right?
Come on. Oh, come on. I'm trying not to be messy with it. Oh my god. Dude.
Go 1 down for -1.
That's always.
Nope. There we go.
It's the first try on their most recent album.
Oh my gosh. Okay. One more 0, right? We have -2x over y, right? So let's go 1, 1. 1, 2.
I wonder if scissors would work better.
Yeah,
Let's try
definitely.
scissors.
It would definitely work better.
You're not
Um,
just,
two.
they just need a lot of love.
It's like,
A lot of for Jude.
oh,
Negative
Negative.
I love how we just left Jacob alone.
I was just gonna.
Okay, we are just.
Yeah.
I'm doing
Yeah.
all the manual labor.
That makes sense.
I think scissors will work better. Sorry.
Let's go 1, 2.
I was gonna say a word.
2 over 2. 1,
Also,
negative
plus
1.
modified by-
Here you go, Solomon. I think scissors work better.
Immediately.
Immediately.
Nope, never mind.
Just
It
kidding.
was one and done.
Two, 1. 4, 1. -4. Booyah.
Oh. Oh, that was
2,
great.
2. 2, 2. 4, 2. -2. Just a little half less.
Yeah. I mean, either way works. Okay, so this
It
one's
should be
one
this parallel.
Oh.
No, it's not, but I don't care. I don't care.
No.
-1, 1. -2
No, it's
over 1.
Just round
Make
down. round
negative
down.
2.
That's it,
I'm gonna
Okay.
-1.
Okay.
There's slope fields on here.
So sorry.
Oh no, we can't get mad.
There you go.
These are all zeros.
Zero.
We still have to do math.
We still have to do that.
There's not a tax.
It's worth it.
there one that's silver?
Do we want to bet that these are positive too?
You know what it is?
Pick one you like.
We have special.
Or these, so this is like, should we want to bet that?
What?
Okay, you get to keep what's left.
Oh, for real?
Laura, do you want the rest of our wiki sticks? Oh my god.
Oh, wait, I don't have like so few left.
What's your function?
No, I have it right here. Oh. I'll let y'all have the.
I don't know.
It seems like we got the easiest function.
Y'all might have. Hey, do me a favor. Take one of the highlighters or pens in your basket, and once you get done, and write your differential equation on the piece of paper so we can look at it. Then you can bring me your card back.
Just, it's like, if you like, you know those, when like architecture teachers will like put toothpicks and marshmallows and build like a structure out of them? That's this, but without the marshmallows. And the toothpicks are big.
That's true.
It's
That's a good assessment.
That doesn't mean it's any less stupid, but.
Very sorry.
It makes it more stupid.
No,
We'll note it.
it makes it.
Because the other one has like joints. This one just.
No.
Okay, you don't have to rip my brain, bruh. Do we want to bet that these are probabilities?
-3 halves.
I haven't let you put a single one on there, have I?
I mean, I don't care.
I've been so mean.
He's hogging the
Sam.
wiki stick.
Why don't you do all of the rest of the work, Sam?
Oh boy. I'm gonna mess it up.
1, 2, 3.
Just make sure this.
Oh, yeah, you're right.
It's gonna be 4, right?
Do they do that test?
That looks like.
Yeah, but I feel like
I'm not gonna comment on
score the highest on the test last year. On the rest.
Why are you so like scared of it? Get your fingers in there. Get your. Oh.
And then this one.
It's gonna be -4.
1, 2, 3.
Like that.
Nice.
And this one. Parallel with that. I thought ours was bad.
Conspiracy theory.
Nice. This one's gonna be parallel to that. Oh, this one.
That sounds about right, Garrett.
This one was like, they don't make like.
No, it's totally not. It's like,
It's all good.
And then up,
Oh, you're so right.
not me.
It's going.
I just wait.
You just left the word out to dry.
X.
Where's the oh marker?
How?
Mind your business.
Nice. Here's the card.
Thank you.
Oh, this is negative. All I'm gonna say is that
He did it.
all I'm gonna say if the slope of those is positive or negative, this is how my actual.
We're the best team I think there ever was.
Obviously.
It'll fade.
I wonder if we can burn that.
That'd be good. Yeah, I mean.
I wonder how long it would last as a wick.
I don't think it'll last that long.
Oh, wick.
Let's get into the wiki, yes.
Parker?
That'd be good.
Yeah.
The pattern's nice.
Yeah. Yep.
Stop putting it down. You got a circle.
How was Friday?
Right, it was KGP. Oh. There's so many. I don't think you need that many.
You know.
What?
I have no idea.
Did what?
I'm just going with it and it makes sense.
The guy from the Disney movie?
Which guy?
There's a lot of guys.
I think it's Tarzan.
I can
Oh.
do it.
Yeah, you do look like that guy.
Yeah, that's not funny.
I realize this because I'm like.
We also have to write off the white eggs.
Everything else.
I just give myself because I'll think about it, come back the next day. and make plans.
All right, you get to keep what's left of your wheat sticks. They've been mutilated beyond recognition.
So on the YouTube thing.
If you don't want them, you can trash them.
Does anyone want my wiki sticks?
Ooh, that would make her fire. That would make her coffee.
All right, we ready? So I want us to take a look at what we all got, because we have very different equations. Okay, yeah, lots and lots of different equations. Okay, in fact, let's just kind of walk around for a second and look at all of them. Talk about what we see. Okay, doesn't this one look nice? It's so nice and neat. Okay, but it's definitely undefined right here because we have nothing, right? So what kind of shape does it kind of look like we're getting? Yeah, it looks kind of circular in nature, but if this is undefined, we're going to talk about what happens with that here in just a second. So I think that's cool. I saw y'all over here looking, which I thought was interesting. The patterns and all that good stuff, like here, it just kind of flattens out right here and it gets steeper everywhere else. No undefined slopes over here. Okay, interesting. Okay, and theirs was they had 1/2 x plus y minus 1. So just several terms added together. Lauren Gareth had a product over here. Okay, it gets that 0 slope and then does something else. Fun times. All right, and ooh, x squared times y minus 1. So we definitely get that 0 up there when y is equal to positive 1, and then anywhere x is 0. So we get 0 lots of places. All right, and then we have a quotient over here. So anywhere y is 0, it would be undefined for sure. Okay, and then we get some 0 slopes when x is equal to -1. Cool. All right, so as we're working through this, let's talk about some of the vocabulary that you can see with a slope field. Okay, so on that next slide, okay, remembering that this is indeed a picture of slopes, if you had to guess, what do you think we might refer to as a null cline? That's an interesting word. Anybody know what null means? 0. These are patterns where our slopes are equal to 0. Okay, and a lot of you were really good, you were good at finding those first, right? Where are those slopes equal to 0? It's one of the easiest ones to do. So we refer to that as a null cline. Okay, and then an isocline. What's an isosceles triangle? Two sides are equal. It's not equilateral. It's 2 sides are equal. So an isocline is where slopes are equal. Okay, so a lot of you are like, oh, well, these are all going to be 1 because that's an isocline. Okay, these are all going to be 0 because that's a null cline. All right, so that's just something they refer to. All right, now the rest of this really falls into what we know about derivatives. Okay, because what we're looking at are slopes. All right, how do we know when an original function is increasing or decreasing? If my slope is positive or negative. So we increase when dy dx, or our slopes, are greater than 0. We decrease everywhere our slopes are less than 0. So that's a picture. All right, so we're going to be able to state those facts. Where is the slope greater than 0? That would be where the function that I don't know is increasing or decreasing. All right, and then how do I define concavity using the derivative, the first derivative, because that's all I have? All right, if dy dx is increasing, okay, wherever it's increasing, that means we are concave up. And wherever dy dx is decreasing, that is where we are concave down. Right? So we're going to be able to look at those pictures and answer those kinds of questions, all right? And some of yours are a lot more difficult to read, okay, your graphs, than the one we started with, okay, because they got a lot more complicated, all right? And the nice thing about a slope field is there are going to be some differential equations that we're not equipped to deal with in Calc 1, all right? But we can still look at solution curves and find where they are increasing or decreasing, or where the function's concave up or concave down based on the slope field when we can't physically or algebraically do or solve the differential equation, which is kind of nice. Okay, so let's look at a few things, all right, a few examples, and there's just a couple more things we need to talk about, and then we'll be good to go, all right? It's all about getting those slopes. So let's look at this one. It says, on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. Take a second and let's do that real fast. Okay, so do example 5. Find those slopes. Negative 2x divided by y. Oh, it happens to be the one Parker and them did over here on the board. Okay, all right. Oh, I don't know. What a coinky dink. All right. So if you need to get up and fill that in, feel free to do so. Okay, because it's over here on the wall. All right, so it should look something like that, right? Here's the strategy I like to show people. I think it's nice when they're filling in a slope field, especially for points that you're given, okay? So you can kind of do a 3-column table there if you plug in your x and y values, all right? And so we can see the slopes as well. If I did 1, 1, all right, that'd be a slope of -2. So things like that, just to show you that, okay? However, if I did 1, 2, okay, that would give me a slope of -1 and so forth, okay? So just as an organizational strategy for when you're doing your slope field, okay? All right, rock and roll. So now let's answer this question. We want to describe where are all the points in the xy plane for which the slopes are positive, okay? So let's think for just a second. Where do we have positive slopes? Which quadrants? Yeah, we got it in quadrant 4. Anywhere else? And quadrant 2, okay? So we could say that we have positive slopes, which would mean the function's doing what? Increasing. So y is increasing when, okay, so in the second quadrant, x is less than 0 and y is greater than 0. And when x is greater than 0 and y is less than 0. Okay, so we're just describing what's happening. All right, where do we have positive slope? It's happening in Q2 and Q4. All right. So let's flip this question around just a second. Okay, so they're going to give me the slope field. They are not going to give me the differential equation. All right, what they're going to ask me to do is to look at this picture to figure out which one of these functions, if I sketched in that slope field, would give me that picture. Okay, so let's talk about the ones that we know what they look like. Okay, so they are giving me the solution curve. Okay, these are the solution curves, which means if I draw the picture, it should look like this equation that's up here. All right, what does sine look like? Yeah, okay, it's our roller coaster. Is that what we have between 0 and 3? No, definitely not. Okay, most of us don't remember ln, so we're going to skip it for a second. What does x squared look like? It's a parabola, a u. Is that the picture we have over here in this line segments? No, definitely not. Okay, so as we look at what's left, what does e to the x look like? Exponential growth. Is that what we have over here? No, so it must be ln. Okay, remember ln. All right, just switches to the side. So that's exactly what we've got over there is an ln type function. If I followed these slopes, right, it would come right around through there. All right, so we have an exponential function. I mean, a logarithmic function, right? So that's what it's asking you to do. Okay, so if they ask you what is the original, okay, not the differential equation, but the original curve, you're trying to figure out which picture graphs onto the one they gave you. Okay, all right, let's look at this one. I think this is an interesting problem, all right? Again, a differential equation. It says let y equals f of x be a particular solution to the differential equation xy satisfying f of 3 equals 4. Okay, then it says to write an equation of the line tangent to f of x at x equals 3 and then use that line to approximate f at 3.1. Okay. If we're going to write the equation of a tangent line, what are those things that we need? A slope and a point. Okay, we need a slope and a point. Well, they gave me the point. The point is 3, 4. Did they give me a way to find the slope? Yeah, I just got to plug it into the differential equation. Okay, so my slope is going to be x over y, which is 4. So now let's write our tangent equation. Y is going to equal, what's my equation going to be? 3/4 minus 3 plus 4. Okay, now what it wants me to do is to approximate f at 3.1. Okay, so we would say f at 3.1 is approximately y at 3.1, and we'd plug it into our equation. 3/4 times 3.1 minus 3 plus 4. Okay, and we get our answer, which I believe is about 4.075 if you plug that into a calculator. Okay. So writing an equation line, of a line of a tangent. Quick, writing the equation of a tangent line. I can't get all that out. Okay. Question on that. Okay. So they can ask you lots of different things. The next thing I want to talk about is drawing solution curves. And for a lot of us, it's difficult. Okay. When we're drawing a solution curve on a differential equation, we're looking for a particular solution. Okay. They will give me a point. All right. We will start with that point. And follow the slopes. Okay, so I gave you an example of a differential equation, all right? and the solution curve through, I think that's -1, -4. Okay? So you can see what it's kind of like. It's following those slopes, weaving between them, all right, following the general pattern. I will tell you this. Anytime you get to a place with undefined slope, you put an open circle. Now, do you see that point up there at 1, 4? Okay, let's kind of mess with sketching that one. All right, and again, there's no perfect science, but you get the general effect of what we want to do. Following those slopes, looks like we level out towards 0. Then we begin to turn and head down. Okay, that way. And then on the other side, we just continue to get more and more steep as we go. Okay, so something like that. You always draw to the end of the slope field. Okay, so you sketch to the edges. Of our slope field. Okay. So this next one was actually part of a free response question, but I believe it was back in 2015, maybe 2013. I could be wrong about the year. It's lovingly referred to as the speedo problem, and I think you'll see why here in just a second. Okay? Everything gets a name. There's the potato problem, there's the spinning top problem. So throughout history, there are things that get named, and we'll hit all of those named problems before the actual exam. Okay. So take a look at this one. All right, so it says, consider the differential equation 1/3 x times y minus 2 quantity squared. Right, so a slope field for that given differential equation is shown below. Sketch the solution curve that passes through the point 0, 2, and sketch the solution curve that passes through the point 1, 0. So let's just kind of look at the pattern of the line segments, okay? Up there where we have 0, 2, what's true about every line segment around it? It's a slope of 0, okay? Everybody got that piece correct, okay? There might have been somebody that missed it, but those of us that got points on this problem, everybody got points for that one, okay? Now, when we get to 1, 0, it gets a little bit more convoluted. So you got to kind of look at what's happening around it. What do you notice about the line segments around the y-axis? Yeah, they're very symmetric, okay? They're very symmetric in nature. And so if I draw one side, it just needs to be symmetric on the other. And they were lenient in that regard, okay? So if we hit right here at 0, 1, if I go up, it looks like it kind of levels out that way, okay? If I go down, it looks like it levels down to about 0, all right? And then what I have to do is make it match on the other side, all right? And that got you full points, as long as you made it match on the other side, okay? Which is nice, all right? Which meant that it had to hit this point as well, okay? And so you're just really looking for how to match. You get why they called it the speedo problem? Yep, looks like a speedo, okay? So it was lovingly referred to. So they gave points right here for symmetry. And that's what they were looking for, right? Did you follow the curves and see that it was symmetric? Okay, so let me show you all the different ways they can ask you this question in multiple choice, all right? Most times when we see a slope field, there's at least one in multiple choice. There's at least one in free response. There are some years where they didn't give us a slope field in free response, but for the most part, we always see one there. Okay? So now let's look at some multiple choice. It says, shown above is a slope field for which of the following differential equations? Right? See what you can do with that one. See if you can figure it out. What are some strategies we could use to try to figure it out multiple choice wise? Like, we don't have time to do every differential equation that's up there. So what could we do? Yeah, let's look at some of the slopes and see what we can do. We know when, so what's happening right here on the x-axis? That means when y is 0, we get a slope of 0. Okay, when y is 0. It also equals 0 when x is equal to what? -1. Okay, so that should help me a little bit. Okay, and so if that happens, does that work for that first differential equation? No. Okay, because I mean it works in those specific instances, but when x is -1, what's the only place that it's going to work to be 0? When y is 0. Okay, is there anyone you can mark off for sure? Yep. Okay, I think A and B we can for sure mark off. And we can mark off E. All right, so now let's work through what we have left. We just need to check a few points after that. Okay, let's check a few points after that. It's going to work when x is 0 and y is -1. I mean, when y is 0 and x is -1, okay? Do I get a slope of 0 for C? Yep. Okay. Because y is 0, so I would get -1 times 0 plus 0. That would work. Okay. If I do it the opposite way, -1 times 0 minus 1, what do I get? -1, so it's not going to be D, it has to be C. So look at those isoclines, look for those nullclines. It will help you on a multiple choice question, okay? All right, let's look at this one. All right, it says the slope field for a certain differential equation is shown above. Which of the following could be a solution to the differential equation with the condition y at 0 equals 1? That means that is an ordered pair. Okay, 0, 1 is going to be an ordered pair on my solution curve. Okay, 0, 1. All right, so let's check and see if that's true at all of these options that they gave me. Okay, chances are it is. All right, is cosine at 0 equal to 1? Yeah. All right, is 1 minus 0 squared 1? Is e to the 0 1? Yep. Is the square root of 1 minus 0 squared 1? Yeah. All right. Is 1 over 1 plus x squared 1? Yes. Okay. So they're going to do that on purpose. So now we've got to think about some other things, all right, that could work to help us. Okay. Now, this is the picture I want to see on the slope field, okay? So I want to see y equals cosine of x. Now, It starts in the right place, but tell me what happens to cosine between 1 and 2. It should cross over the axis, right? It should cross over the axis. And we do get a 0 slope right there, okay? But if we notice, this thing is leveling out, all right, before. So it can't be that cosine, all right? What does 1 minus x squared look like? It's a semicircle. Yep. Is that the picture we have right there? Nope. Okay. What about e to the x? What does it look like? That's exponential growth. Okay. That's not what we got right there. Okay. What about square root of 1 minus x squared? Yeah, that's your semicircle. Sorry. Yep. That's your semicircle. And this was an upside down parabola. Okay. So we don't have a semicircle. So it leaves me with the last one. Okay. It leaves me with the last one. You may know what that one looks like. I don't really off the top of my head know what that one looks like. Okay. Yeah, it's what it's going to be. So we have to use what we know, all right, to make it work. Now, another strategy you can use is to take the derivative of all of those and plug in that initial condition and see who works, okay? So another strategy for that is to take the derivatives and plug in the initial condition. Right, so there's another strategy for you for that one. Okay. All right, last one. Okay, last one. It says, consider the differential equation x plus 1 over y. So they drew it out in certain points. While the slope field in part A is drawn at only 12 points, it's defined for every point in the xy plane for which y does not equal 0. Okay, for which y does not equal 0. Describe all the points in the xy plane, y not equal to 0, for which the derivative is equal to -1. Okay, so where is this derivative equal to -1? So quadrant 4. All right, so let me show you something. What do they tell me dy dx equals? -1. So I'm going to take this differential equation, and I'm going to take the dy dx out, and I'm going to put -1 right there. Okay? Because we want to describe where these points are going to happen. All right? Well, let's just solve for y. Y is a function of x. So that would give me -y equals x plus 1. And what would y equal? Yep. Okay. So that is where the derivative would equal -1, as long as y is equal to -x minus 1. So we would say the points in the xy plane where dy dx equals -1 occur when y is not equal to 0 and y is equal to -x minus 1. Okay, so we just plug in whatever they want the derivative to be and solve for y. It's the easiest way. That way you don't miss any points. Okay, you don't miss any points that way. All right, slope fields, what questions do you have? They're just pictures of differential equations. You're drawing little slopes of line segments. Okay. Did you like doing them on the big paper? It's the first time I've ever done that.
Yes.
Okay. All right. I think it's a good visual. Yeah, I think it shows you better than just drawing on your own paper. I agree. Okay. All right. All right, here we go. So your lesson practice today is that slope field packet, but only do the even ones. Okay, only the even ones. Tomorrow you will have a really quick quiz. It's 4 questions, maybe 5. Put a quick quiz. All right, over slope fields. Okay. You'll be given a differential equation. You'll be given slope fields. You have to match them. Okay. So it's a quick quiz. It's matching. All right. Over just what we did today. Okay. You do have a wrap up on Google Classroom, so let's do that really quickly. Okay. And then you'll be good to go for the day. Don't forget, try to come in and do your second round of test corrections if you want to by Thursday. Yeah, give me just a second.
Yeah, you're okay. Take your time.
Okay, do your wrap up. Don't lose that point.